Section 4.3 Graphs of Polynomials. In this section we're going to take a look at how to graph polynomial functions, that is, functions that are polynomials. And just a quick recap, polynomials are algebraic expressions where the exponents are either positive integers or zero. Okay, so the exponents cannot be a decimal or a half or a negative number. So we've already done some of this before, so let's quickly recall some of the stuff we've already done. Okay, first, let's say if I give you the simplest polynomial like this, p of x is equal to b. That is, if you replace the function notation, instead of f we have p here, and write it as y, we have y is equal to b. We know what this looks like. This is a horizontal line. That passes through b. Okay, because this is a line where y values are always b and x can be anything. We've done this before in chapter 3. Then the second type of polynomial we can talk about is this one, mx plus b. Out here the degree is 1. M and b are just some numbers. We know what this looks like too if I write it in terms of y is equal to mx plus b. This is just a graph of a line also. Since the degree is 1, it's linear. And we know how to graph a line. In chapter 3 we learned 3 different ways to graph a line. We can randomly pick 2 values of x and then find 2 corresponding values of y, so we get 2 points on the line and connect them. Or we can also find the x and the y intercepts of the line and join those to create the line. Or we can start with the y-intercept and then use the slope to find the second point, and then once we have the second point we can connect the y-intercept and the point to graph the line. So we have 3 different ways to graph the line. Then in chapter 3 we also learned how to graph quadratic polynomials. So we have something like this, ax squared plus bx plus c. Quadratic means degree 2. That is, we can replace p with y, so we get ax squared plus bx plus c. And we found that the graph of this was a parabola. And to graph a parabola, we basically had to find the x and the y intercepts. We had to find the vertex of the parabola where the parabola turned, and that's pretty much it. That's all we had to do. And then we could use a little symmetry about the parabola to graph it very quickly. Okay, so we already know how to graph 3 polynomials. We use a constant polynomial, degree 1 polynomial, degree 2 polynomial. So we already know how to do that. What we want to do in this section is, now, what happens if you have a polynomial of, not p of x, polynomial of degree 3 or higher? We already know how to do all the other degrees so far. Degree 0, degree 1, degree 2. So what happens if you have a polynomial of degree 3 or higher? That's where this section comes. So that's what we're going to learn today. Section 4.3. Okay, so today we're going to learn how to graph polynomials of degree 3 or higher. Alright, before we do that, let's just talk about polynomials for a second. There's certain things about polynomials we need to learn. Okay, some properties of polynomials. Okay, the first is, okay, polynomial functions. Graphs of polynomials and polynomial functions. Graphs of polynomial are continuous. Continuous means there's no gaps in them. So they're continuous and smooth. That means there's no sharp edges to them. That means a polynomial graph cannot look like this. There's a sharp edge here. Okay, or it can't look like this, and so on. Okay, so graphs of polynomials are continuous. That means they have no gaps. Continuous means no gaps. Okay, and smooth, that means no sharp edges. Okay, I shouldn't say edges, but corners is more correct. Okay, so that's one thing that's very nice about polynomials. So basically, what does that mean? Polynomial graphs just roll. They just roll because they're nice and smooth and they're continuous. Okay, So they just roll. The second thing you need to know about the polynomial graphs is the the number the number in, actually let's write it this way. The graph of a polynomial of degree n has at most n minus 1 turns. Okay, so the number of turns that a polynomial has are at most n minus 1. So for example, earlier we talked about a parabola. A parabola looks like this, and the degree of a parabola is always what? 2. So how many turns can a parabola graph have? 2 minus 1, because if the degree is 2, it's n minus 1, so 2 minus 1 is 1. It has 1 turn. You can see turn once. Okay, so that's what it says. The third property of polynomials are the graph of a polynomial of degree n has at most, it cannot have more than that, but has at most n zeros. Actually, let me n, not zeros, x-intercepts. And you'll learn in a little bit, x-intercepts are the same thing as zeros or roots that we talked about once before in the last section. Has at most n x-intercepts. So for example, again, just referring back to the quadratic polynomial might look like this. It is degree 2, so it can have at most 2 x-intercepts. It can't have more than that, but it can have less than that. In this case, we have 1 and 2. We have 2 x-intercepts. Okay, or it could be a parabola like this, then it only has 1 x-intercept. Or it could be a parabola like this, but it has 0 x-intercepts, but it can't have more than 2. Okay, so those are the things about the polynomial graph you should always know. 3 things about polynomial graphs. The first one is the most important one. They're continuous and smooth, because that's what's going to make it easy for us to graph polynomial functions. Okay, all right. One other thing we want to talk about, just not polynomial graphs, but any graph for that matter. Okay, actually let's talk about graphing polynomials. Okay, this is C, right? Yeah. Graphing polynomial functions. Okay, so let's do that. Anytime you want to graph a polynomial function, the first thing you want to do is find the x and y intercepts. We've talked about how to do that. To find the x-intercept, you set y to 0, and to find the y-intercept, you set x to 0. Okay. Now, the second thing you want to do is you want to find the extreme behavior. We'll talk about that in a second. Extreme behavior. And that's it. We just have to do 2 things to graph a polynomial function. We have to find the x and the y intercepts, the extreme behavior, and we're done. Okay, so let's talk about the extreme behavior. Okay, what does that mean? Okay, so basically what that means is what happens. Actually, I'll just put a note. I'll abbreviate extreme behavior EXT, BEH. The extreme behavior captures the direction captures the direction of the graph as x values get very big. And when I say very big, imagine the biggest number in your head, and very small. So basically we are talking about when x values get very big, we are talking about the behavior to the right, because as we go to the right the x values are getting bigger and bigger. And when we talk about x values getting very small, we are talking about the behavior to the left. As you go to the left, x values keep getting smaller and smaller. Okay, so that's what the extreme behavior captures. So how do we do that? So to find the extreme behavior, keep the dominating term of the polynomial. And that makes sense. Let me give you an example to show you how to do that. So this is how we find the extreme behavior. So here's an example to show you. Let's say if I have p of x is equal to 2x cubed minus 3x plus 5. Okay, now just imagine x is the biggest number in your head. Imagine the biggest number in your head. Now if you take and replace x with that big number, which of these three terms is going to have the largest impact in the polynomial, in the behavior of the of the graph of the polynomial? Which of those three terms is going to dominate? Well, even if you think about 100 itself, let's take 100 itself. 3 times 100 is just 300, 5 is just 5. But if I take 100 cubed, okay, and multiply that by 2, that's a big number, and that number is going to be the one that's going to dominate this polynomial. That's going to control the behavior of this polynomial. So when we're trying to find the extreme behavior, we're only interested in the dominating term. So what I can do is I can write this polynomial this way: 2x cubed. I can ignore all the other terms. So once I do that, now I want to know what happens to the right and what happens to the left. The only way I can imagine that is by doing this. When x gets very big, so let's imagine x goes to plus infinite. So then what happens? We get 2 times infinite cubed. Well, infinite cubed is infinite. Multiplied by 2, that's still going to be infinite. So remember, p is the same thing as y. So what does that tell me? Y goes to plus infinite. On the other hand, when x goes to the left, when x gets really small, imagine it's going to minus infinite. We get 2 times negative infinite cubed. So negative infinite cubed is negative infinite times negative infinite times negative infinite. It's going to be negative infinite. It's going to be a big number. It's still going to be infinite. If you square infinite, it's still infinite. It's still a big number. Okay. So in this case, y goes to negative infinite. So we know that when x gets really big, y gets really big. It goes to plus infinite. When x gets really small, y gets really small. It goes to negative infinite. That means the graph's going down, because when you look at the y-axis, this is when the y goes to infinite. This is when y goes to plus infinite. Y values are getting bigger this way, smaller this way. So we know the direction of the graph. So that's what extreme behavior does. It basically captures the direction of the graph when x gets really big and really small. So it's important that we capture that. Okay. Now, one other thing to note, so that's one note about extreme behavior, and this is how we capture extreme behavior. When I do some examples, you'll get a better idea too. But all we do is keep the dominating term that has the highest power, and then you take a look at what happens when x gets big, and you denote that by plus infinite, and you find out what happens when x gets small, you denote that by minus infinite, and you see how the graph behaves. Okay. The graph in this case goes up when x goes to the right, and out here when x goes to the left, the graph goes down. That's all we need to know. Okay, I'll come back and do some more examples, but there's one other thing I want to talk about. Note about multiplicity. So this is about extreme behavior. Okay, so this is about extreme behavior. Then we need to talk about multiplicity. Okay, so this is very important. So let's talk about that. If this only applies to x-intercept, if the x-intercept has even multiplicity, remember multiplicity is what? The number of times a zero repeats, you know? Okay, so if it repeats even number of times, okay, then the graph of a the graph turns at that x-intercept. I'll abbreviate that int. So if a graph has even multiplicity, if the x-intercept has even multiplicity, then the graph is going to turn at that x-intercept. Okay, so here's a quick example of that. So let's say the x-intercept is this. We have 2, 0 and 2, 0. So you can see this x-intercept repeats twice. Okay, so in that case, how does a graph behave? At 2, the graph is going to turn. It's going to go like this. Okay, that's an important thing to note. Now what happens if it has odd multiplicity? If the x-intercept, I'll just abbreviate int, has odd multiplicity, then the graph flattens at that x-intercept. Okay, so in that case the graph will flatten there. So here's an example of that. Let's say we have an x-intercept that is like this. We have 1, 0, 1, 0, 1, 0. So it repeats 3 times. So it has odd multiplicity. It's repeating 3 times. So in that case, what happens at 1, the graph will flatten. It'll come like this. It'll go a little bit flat here. Go like this. So that's what the graph does. Okay, so if it has odd multiplicity, it'll flatten. If it has even multiplicity, it'll turn. Okay, that's everything we need to know about graphing polynomials. And that makes it very easy to graph polynomials. So let's start by taking a look at a few examples. So let's say they've asked us to graph the following polynomials. Okay, so here's the first one. So they've given us p of x is equal to, we have x cubed minus 3x squared. Okay, so what were our requirements to graph a polynomial? What did I say we had to do? 2 simple steps. Find the x and the y intercepts first, and then find the extreme behavior, and you're done. Okay, so let's do this. So to find, the first thing we're going to do is find the x-intercept. To find the x-intercept, if you recall from chapter 3, we set y to 0. Okay, so in this, y is just the same thing as this. Just remember that when we are talking about functions. So we get 0 is equal to x cubed minus 3x squared. Now, if you recall, just to tie things together, when we set y to 0, that is the same thing as setting p of x to 0, because p of x is the same thing as y. So finding the x-intercept is the same thing as finding the zeros or the roots of p of x. Just to tie in some stuff that we did in section 4.2. So when we're talking about x-intercepts, we're really talking about zeros or roots of p of x, because when we set y to 0 to find the x-intercept, we are setting p of x to 0. and we set p of x to 0 when we're looking for roots and zeros. So let's do this. I've told you before, anytime you have degree 3 or higher, the only way you can solve something like that is by factoring. So let's factor this. What's common in the two terms? X squared. So we get x minus 3. This product is 0, so it tells me what one of them has to be 0. So we get x is equal to 0. X minus 3 is 0. X squared is 0. That tells me what x times x is 0. So we get x is 0 and x is 0. And over here we get x is equal to 3. Remember to do this. Students always forget, they just say x is 0 once. This is important. So what are my x-intercepts? By the way, this has multiplicity, what? This 0, 2. This has 1. So my x-intercepts are 0, 0, 0, 0. Because when x is 0, y is 0. When x is 0, y is 0. It repeats twice, so I need it twice. And then we have x is 3, 0. So those are my x-intercepts. Since these guys repeat twice, even multiplicity, then the graph is going to turn there. We know that from earlier discussion today. Okay, so I'll just put that there. That's about it for the x-intercepts. We are done. Okay, next we want to find the y-intercept. How do we find the y-intercept? We set x to 0. So we get y is equal to 0 cubed minus 3 times 0 squared. So we get 0. So my y-intercept is just 0, 0. When x is 0, y is 0. Okay. The next thing I want to do is the extreme behavior. If you recall, how do we do extreme behavior? We keep the dominating term. So we have p of x. So what is my dominating term in my polynomial? It's just x cubed, because out of these two terms, this is the one with the higher exponent. So this is the one that's going to have a larger effect in the long run. So we get x cubed. Okay. Now we want to see what happens when x gets really big and when x gets really small, because we are trying to trap this behavior. When x gets really big, how does the graph behave on this side when x is really, really big? Okay, and we also want to know what happens on this side when x is really, really small. So I want to know what's happening on the sides. In the middle, the x-intercept is going to help us figure that out. The middle is going to be figured out with the x-intercept. It's the extreme behavior on the other two sides. On the right and the left side, we want to know what's going to happen to the graph. Okay, so let's take a look at that. To figure out what happens to the right, remember p is the same thing as y. I take x goes to infinite. So I have infinite cubed. Infinite times infinite times infinite is infinite. So on the right, when x gets really big, goes to the right, y gets really big, so the function's going up. And when x gets really small, that means you're going to negative infinite to the left. Then what do we get? We get negative infinite cubed, which gives me negative infinite. So in that case, y gets really small. It goes to minus infinite, so it's going down. So that's all we need to trap here, the extreme behavior. Okay. Now that we have all the tools to graph it, let's graph it. Okay. Always label things when you're graphing stuff. So it's a good habit to get into. Okay, make your graphs look nice and easy to read. I have 1, 2, 3, 4, and then we have minus 1, minus 2, minus 3. Then we get 1, 2, minus 1, minus 2. Alright, so the first thing we do is start with our intercepts. My x-intercepts were 0, 0, and 3, 0. And 0, 0 repeated twice. So it was this point, this point, and I'll put a t there because that's where it's supposed to turn, because it has even multiplicity. And my other x-intercept was this. This wasn't special, it was just regular x-intercept. Okay, then I know that my graph to the right, when x goes to the right, it's going up, so it's going up here. And to the left, when x gets really small, minus infinite, when x goes to negative infinite here, the graph's going down because y values are getting smaller and smaller. So this is what my graph looks like. So let's think about it. In the middle, how is the graph going to look? I already know what it does on the right and the left. In the middle, the graph is, according to our properties of polynomials, what was it? The graph is going to be continuous and smooth. It's just going to roll. Okay, so let's do that. So let's say we start here at the bottom, and then we have to come to this point somewhere along the way. Okay, so we come over here, then we're going to turn there. Okay, now I'm going to come here, I'm going to turn, then I'm going to keep going this way, but I can't keep going that way because I have another x-intercept I have to pass through. So somewhere along between 0 and 3 the graph has to turn. So let's say it turns here, and then it passes through that point, and there's your graph. So there's your graph of that polynomial. Okay, now this graph is fairly good. There's only one thing missing with this graph. Okay, like I said, I just mentioned a minute ago, between 0 and 3 it has to turn again to go through the other x-intercept. We don't know where it turns. My graph could have looked like this. It could have gone like this, or it could have also gone like this. Okay, we don't know where it's going to turn. To do that, to figure that out, we need calculus. So for now, we'll just guess somewhere in between where it's going to turn. We don't have, these are rough sketches, so we don't have to be very accurate about it. We just want to get the general shape of the graph. Now, a couple things to just point out. Okay, I purposely told you the graph starts here, and then basically we use the x-intercepts and the y-intercepts to connect the dots. Okay, now the graph could not have gone up like this and like this, because then I would have another x-intercept here. Did I find another x-intercept? No, I only found 2. So we know it has to go through these 2 points, and at this point it has to turn. So we start out here, it turns, then it turns here because it has to go through that point. Okay, now how many turns does this graph have? It has 1, and 2 turns. What was the degree? The degree was 3, so it should have n minus 1 turns at most. So it had 2 turns. Okay, so that was correct. How many zeros did it have? Okay, it had, according to a note earlier, what did we say? It had at most, a degree was 3 in our case, so it should have at most 3 zeros. In our case, we had how many zeros? 2. 1 and 2. The zeros are the same as x-intercept, and I just proved that to you right here. They're the same. X-intercepts and zeros are the same, so it had 2 zeros. Okay, let's take a look at a couple more examples just to make sure that we understand the ideas. Okay, let's say if I've given this is 2. We're given p of x is equal to, we have x cubed, x to the 5th, minus 4x cubed. Okay, so let's do this. Alright, the first thing we do is find the x-intercept again. To find the x-intercept, what did we do? So we said y to 0. Y is the same thing as this. So we get y is equal to 0. So we get x to the 5th minus 4x cubed is equal to 0. So now how do we solve that? Well, anytime you have degree 3 or higher, we have to factor. This is degree 5. Okay, so let's do that. So we take out a x cubed. We get x to the squared minus 4 is equal to 0. This product is 0, so one of them has to be 0. So we get x cubed is equal to 0, or x squared minus 4 is equal to 0. Now x cubed is equal to 0 tells me what? X is equal to 0, or x is equal to 0, or x is equal to 0, because cube means what? X times x times x. I have 3 zeros, because you'll end up with what? X times x is 0. So again, this product is 0. That tells me what? One of them has to be 0, and that's how we get those. Okay. On this side, I have a square and a number. How do I solve an equation that has square and a number? We move the number on the other side and take square roots. Anytime you take square roots, we have to introduce plus or minus 2. What's square root of 4? 2. Okay, so those are my zeros, or x-intercepts. So let's write them down. We have 0, 0, and I'll put a 3 over here to denote the 3 multiplicity. So and that tells me it's going to flatten there. Okay, then my other one is 2, 0, and my other one is minus 2, 0, and those are not special. So these are my x-intercepts, and you can see them from here. These are 3 of them, then I have 2 of them here. Okay. Now earlier we learned that the number of zeros of a polynomial is equal to the degree of that polynomial, and in this case the degree was 5, so we had 5 zeros, 1 2 3 4 5. Okay. Next we want to find the y-intercept. To find the y-intercept we set x to 0, so this implies we get y is equal to 0 to the 5th power minus 4 times 0 to the 3rd power, so we just get 0. So my y-intercept is just 0 0, because y is 0 and x is 0. So we did that. Next we want to do the dominating terms. So what's my dominating term here? Out of the two terms, the biggest impact is going to be felt by x to the 5th. Okay. So now I want to see what happens when x gets really big, goes to the right. I get infinite to the 5th power is still infinite, so it goes up. Y gets bigger. If x gets really small, if x goes to negative infinite, then we get negative infinite to the 5th power. That gives me minus infinite. That means it goes down. And it's not always this case. I did 2 examples where it just so happened that's what we ended up with. But you could have it going up on both sides or going down on both sides. It depends. Okay. Now we're ready to graph. We did our 2 things. Okay. So I have 1 2 3 minus 1 minus 2 minus 3, 1 2 minus 1 minus 2. So let's just plot our x-intercepts first. We had x-intercept at negative 2 and 2, and also at 0. This one was a special one, so I'll put an F there because it flattens that repeated odd number of times. When the x-intercept repeats odd number of times, then it flattens there. And then we know that on the right, as x gets really big, y values get really big, so the graph goes up. When x gets really small, the y values get really small, the graph goes down. So in the middle, the graph is just going to roll and keep going through those x-intercepts. Okay, so let's graph this. So it starts down here, then it's going to go through my first x-intercept. You always go from left to right, and then it has to go through my next x-intercept, which is at f. So somewhere in between negative 2 and 0, it has to turn. So you don't know where it's going to turn, so let's assume it turns right here. And because it's supposed to flatten here, it's going to come over here, go like this. And then it's going to turn again because it has to go through the next intercept, and then it goes up. There's the shape of that graph. Okay? Alright. So if we did not know this idea of flattening, we would not know that's what it does there. Okay? Let's take a look at 2 more examples and then we'll be done. 3. So let's say if you have p of x is equal to x, negative x, times x minus 1 cubed, and then we have x plus 2 squared. Okay, let's just take out this minus. Let's put that in. Okay, that's what we have. So let's find the x-intercept. To find the x-intercept, we set y to 0. Okay, so we get 0 is equal to negative x, x minus 1 cubed, x plus 2 squared. Now this is already factored. You can see it's already written as a product, so we don't have to factor this. It's all done for us. We just have to find out what happens. The product is 0, so it tells me x is equal to 0, this x, or x minus 1 cubed is equal to 0, or x plus 2 squared is equal to 0. One of them has to be 0. This tells me 3 things. X minus 1 is 0, x minus 1 is 0, or x minus 1 is 0 because of the cube. Because this is the same thing as x minus 1 times x minus 1 times x minus 1 is 0. So each one gives me x is equal to 1, 1, and 1. Over here, x plus 2 times x plus 2 is 0 because of the square, so one of them has to be 0. Okay, so we get x is equal to negative 2 and negative 2. So now we have 1, 2, 3, 4, 5, 6 x-intercepts. So let's write them down. We have 0, 0. Then we have 1, 0. That repeats 3 times, so it flattens there. Then we have negative 2, 0. That repeats 2 times, so it turns there. So those are my x-intercepts. Okay. Now before I go any further, let me just go back to this one. The degree of this polynomial was 5. So according to the chart properties of polynomials, it should have 5 minus 1 turn, so at most 4 turns. Okay, so let's see where they are. There's 1 turn here. Then over here, if you notice, like it's going like this, so there's a turn there technically. And then it's going like this, so there's another turn there. And there's a 4th turn here. So there's 4 turns. Okay, the 2 turns are hidden in here because out here it looks like it's going down, then it turns and goes like this. So there's actually 2 turns in there. Okay. Alright. So I found my x-intercept. To find the y-intercept, what did we do? We set x to 0. I do want to stress this. All 3 examples I've done so far, the y-intercept has been 0. The next one I'll do, I'm like sure it isn't. So we get y is equal to negative 0 times 0 minus 1 cubed, 0 plus 2 squared. Since we are multiplying this whole thing by 0, the answer is going to be 0. So my y-intercept is 0, 0. Okay. The next thing we want to do is the extreme behavior. Now comes the interesting part. What is my dominating term here? Okay, well let's go back and take a look at it. Well, out here I have x. I'm multiplying that by this guy. So the biggest term in here is going to be x cubed plus something something. When you expand that, out here the biggest term is x squared plus something something. And then I have minus x here. So if you distribute this, what do we get? Negative x times x cubed is negative x to the 4th. Negative x to the 4th times x squared is negative x to the 6th. So my dominating term here is negative x to the 6. So now let's see what happens when x gets really big. So it goes to infinite. I get infinite raised to 6. Any infinite raised to 6 is just infinite. There's a negative on the outside, so I get negative infinite. Now what happens when x gets really small? Okay, in that case I get negative infinite raised to 6. Any negative number raised to even power is always positive, so you get positive infinite to the 6th. Multiplied by negative, you get negative infinite. Okay, so now in both cases, when x gets big, y gets small. When x gets small, y gets small. So in both cases the graph's going down. So let's go ahead and graph this. Okay, we have 1, 2, 3, minus 1, minus 2, minus 3. Okay, so let's plot stuff. My x and the y-intercepts were, my x-intercept was 0, 0, 1, 0, negative 2, 0. Okay, 0, 0, 1, 0, negative 2, 0. This is where it flattens. Always put an F there, and this is where it's going to turn. So if you put those reminders for yourself when you graph it, you'll remember those. Then we know that when x gets really big, the graph goes down, so it's down here. When x gets really small, the graph goes down, so it's down here. So it's going to start here, then it's going to go through all my x-intercepts and turn and flatten accordingly. Okay, so it starts out here. Okay, it's going to turn here because it turns at that x-intercept. Then between negative 2 and 0, it has to turn again because it has to go through my x-intercept of 0. So it's going to go through there. But then it has to turn again because it has to go through 1. And it has to flatten at 1, so it's going to come out here, it's going to flatten, and then it's going to keep going down. So that's what that graph looks like. Okay, let's take a look at the number of turns. I have 1, 2, 3, and then there's 4 here and 5 here. So there's 5 turns. The degree was 6. We should have 5 turns, n minus 1 turns, and that's what we have. Okay. So you can see that. So that's how we graph this. And again, I do want to stress this. The only thing we are not sure about is over here, does it go like this? Or does it go like this? We don't know where it turns in between -2 and 0, but we do know it turns. Same here, whether it goes like this, and so on. Alright, one last example. Let's do one where we do have an y-intercept. So let's say if you have p of x is, we have 2 minus x, and we have 2 minus x squared, and we have x plus 3. Okay, so let's say I want to graph that. Alright, so let's take a look at this. Okay, let's make this x plus 3 and x minus 3, and let's make that a 1. Okay, alright, so I want to graph this. So the first thing I do is find the x-intercept. So we set y to 0, and in this case again the polynomial is already factored. You can see that we don't have to factor this again, so that's really nice. Okay, this is already written as a product. One of them has to be 0. Okay, so let's do that. So we have 1 minus x squared is 0, so we get 1 minus x is 0, or 1 minus x is 0 because the base is multiplied by itself twice. So we get x is 1 and x is 1. I hope you guys can realize that, because this is 1 minus x times 1 minus x is 0. Over here we get x plus 3 is 0, so we get x is equal to -3. And we get x minus 3 is 0, so we get x is equal to 3. So we found 1, 2, 3, 4 x-intercepts. So let's write them down. We get x is 1, y is 0, it repeats twice. When x is -3, y is 0, and when x is 3, y is 0. Okay, these are my x-intercept. It turns here because of the even multiplicity. Okay. To find the y-intercept, what do we do? This time we do have a y-intercept, so let's do that. We take and set x to 0. We set x to 0 to find the y-intercept, so we get y is equal to, we get 1 minus 0 squared, then we get 0 plus 3, and we get 0 minus 3. So we end up with 1, because 1 squared is just 1, 0 plus 3 is 3, and 0 minus 3 is minus 3. So we end up with -9. So my y-intercept is x is 0 and y is -9. So there's my y-intercept. So we did find a y-intercept this time. Now also comes another interesting part of finding the extreme behavior. So what's my dominating term? What's the term that's going to have the largest effect here? Well, let's take a look at this. If you were to expand this, okay, because you have a square on the top, the dominating term would be x squared with some terms in the front. Okay, out here we have x, the dominating term. Out here we have x. So if you multiply x times x times x squared is x to the 4th. So my dominating term is x to the 4th. So now what happens to x when, what happens to y when x gets really big? Goes to plus infinite. We get infinite raised to 4 is just infinite. What happens to y when x gets really small? Minus infinite. So we get minus infinite raised to 4. You take negative infinite times negative infinite 4 times, we get just plus infinite. So in this case, when x gets really big, y goes up. When x gets really small, y still goes up. Okay. Alright, so we have all our tools to graph now. So let's graph. We had 3 x-intercepts. I'll scale this by 3's. Okay. So let's plot our x-intercepts. My x-intercepts were 1, 0, negative 3, 0, 3, 0, and it turns at 1, 0. It's 1, 0 minus 1, 1, 0. So 1, 0, it turns there. 3, 0, negative 3, 0. Then my y-intercept this time was at 0, negative 9, so it's right here. Okay? And we know that when x gets really big, the graph goes up. When x gets really small, the graph goes up. So in both of these cases, the graph's going up here and up here. So we start out here on the left. We start at the top here. It's going to go through my first x-intercept. So it's going to come out here, go through my first x-intercept. Then it has to go through this x-intercept, the next one. We always go from left to right, but then it also has to go through this y-intercept. So we know that it's going to come over here like this. Then it's going to turn and go through the y-intercept. Okay. And then it's going to come and turn right here. Okay, let me draw this a little bit better. So let's say it comes like this. Again, we don't know where it's going to exactly turn, but let's say it turns right there. It's going to go like this, then it's going to turn again at this x-intercept. And then between 1 and 3 it has to turn again because it has to go to the next x-intercept. So it might go like this. There's a graph of that function. Okay. So we did find a graph that had a y-intercept. All you have to do is just practice these problems, follow the guidelines that I've given you, and you should be able to graph every single polynomial function by using just those guidelines.